All right. We're going to be writing an essay on cardiac cycle, and this is going to be the outline how to use it. An introduction, mid to late diastole, atrial systole, ventricular systole, and early diastole. These are the 4 stages which I'll be using to discuss the cardiac cycle. There are different parameters that people might want to use, but this is what I'll be using for the essay. And also, I'll add here clinicals. I think I'll add here clinicals. That will also help you for your exams. Clinical physiology, clinicals. Now let's begin. What is going to be the introduction of the cardiac cycle? I will say the cardiac cycle are the mechanical events. The mechanical events that occur in the heart. The mechanical events that occur in the heart. Now, actually, the mechanical events in the heart happens to be the manifestation of the electrical activity that happens. Now, when we see all these movements of ions and all that, and then muscles can contract and relax, that is going to predispose the heart to mechanical activity. So this also means something. If you do not see write an essay on the cardiac cycle, when you see write an essay on the mechanical events of the heart, same question that is still being shown to you. Just a change in words, that an essay on cardiac cycle can also be framed as an essay on the mechanical activity of the heart. So the first statement was that cardiac cycle happens to be the mechanical events that occur in the heart. Now the second statement is that we are going to use an arbitrary point, and this helps us to divide it into 4 phases. And what are those 4 phases again? Phase number 1, mid to late diastole. Phase number 2, atrial systole. Phase number 3, ventricular systole. Phase number 4, early diastole. These are the 4 phases which I'll be using to describe the cardiac cycle. So you list them out. So list them out again. Mid to late diastole. You list the next one, atrial systole. You list ventricular systole, and then early diastole. You list it out. Now begin with number 1, which is the mid to late diastole. Mid to late diastole. Now, what are important points to add here? For mid to late diastole, which is the first one here, what are the most important points to state here? Number 1, we are going to say that, maybe let me show you something like this. We have something that looks like this. We have our atrium, and then we have our ventricle like this. So I've shown you just one half of the heart. This is the half of the heart. Then this is the atrioventricular valve. The atrioventricular valve can either be the bicuspid or the tricuspid. Then on this other side, you are going to have another valve. This valve that is on this other side is what we call the semilunar valve. The valve that extends through the larger arteries. The larger arteries, I mean aorta on the left or pulmonary artery on the right. Maybe let me show you what I'm saying for easy understanding. I say we have something like this. This is the right ventricle, right atrium, left atrium, and left ventricle. The aorta comes out like this. This is the aorta, the large artery on this other side. Then on this other side, the 2 large arteries here that was entering here were the superior and inferior vena cava. This is just the topography of how the heart looks like. Are we together? Then, taking out from this portion, going upwards here, we're going to have an artery. And this artery goes to the 2 lungs. And that artery is called the pulmonary artery. So this is what I want to show you here, like this, like this. So watch it again. This is pulmonary artery. It is the outflow artery on the right side. This is the aorta. The aorta is the outflow artery on the left. Then, what were the inflow arteries, the inflow vessels, on the right? The inflow vessels were either the vena cavas, superior and inferior vena cava. What were the inflow vessels on the left? The pulmonary vein. The pulmonary vein. So those are things to note here. So what I'm trying to say is this, that I will show you atrium, and then I'll show you ventricles. Are we together? So I was trying to show you. So what happens in mid to late diastole? Number 1, you are going to say that pressures are very low. Pressures in the atrium are low. pressures in the atrium and ventricle are very, very, very low. That's the first point. Now, because these pressures are low, blood only moves passively into the ventricles, passively. When we say blood is moving passively, it means that the atrium is not contracted. It is just being a relaxed state. So blood moves passively into the ventricles, moves passively. So I put that in underlying form so that you know what I'm saying. All right. And very important, it is this state that contributes to 70 to 80% of ventricular filling. 70 to 80% of ventricular filling is a constituent of mid to late diastole. So 3 points I'm going to put here. Point number 1, pressures are low. Point number 2, blood is moving passively. Point number 3, it contributes to 70 to 80% of ventricular filling. Now, what next do we have? Number 2, the second point should be atrial systole. Now, what am I going to talk about in atrial systole? For atrial systole, number 1 is that systole means contraction. So in this case, the atrium is contracted. So number 1, the atrium is contracted. The atrium has begun contracting. All right. Now, number 2. What is number 2? Number 2, this one should contribute the remaining portion here. If 70 to 80% have been contributed by the mid to late diastole state, the remaining 20 to 30% of ventricular filling comes from atrial systole. So 20 to 30% of ventricular filling. So the remaining 20 to 20%, we are going to squeeze it. We squeeze it like this. The atrium is squeezed out, and then it fills the ventricle. Now, the third point that is necessary is that the total blood that we see at the end of atrial systole is what we call the end diastolic volume. An end diastolic volume is about 140 mils. Very true. So this is what you say here in mid to late diastole. This is what you say in atrial systole. About 3 points to go. Now let's go down to the next, which is ventricular systole. It has lots of information to say here. Now, but I think I should add something here before, so making it 4 points. And that is going to be that it corresponds with the P wave of the ECG. Corresponds with the P wave of ECG. All right. So let me leave all this and then let's talk about ventricular systole. Now, for ventricular systole, I'll be talking about ventricular systole from this side. Number 1, from ventricular systole. Now, in ventricular systole, if you watch, the first thing that you must tell us is what is the ECG equivalent. Now, let me show you something. This is how the ECG looks like. It looks like this. So this is the P wave. This is going to be the here ROS complex. This is the T wave. So what happens is that this particular one was the one that corresponds to the atrial systole step, which I've talked about. Now, near R wave and just after T wave, that's around here and here, is what we consider as the step of ventricular systole. So in ventricular systole, what are you going to talk about? It begins at R wave, and when will it end? It will end just after T wave. Just after T wave of the ECG. Right. So that's the first point. Where the ventricular systole begin? It began at R and will end just after T waves. Now the second point that is quite necessary to say, maybe let me remove this one here for better illustration and for you to really understand what I've been saying. So in the second point here, maybe I show you how that heart looks like that again. Maybe clearer than this one here. We have our ventricles like this, and then we have our valves, and then we have valves that look 3 number. So this one here is on the right side. This one here is on the left side. So on the left side, we have the bicuspid, On the left, we have the tricuspid. So both of them are also called atrioventricular valves. So the second thing that happens in ventricular systole is that as we have filled the ventricles, ventricular pressures are beginning to build up. And they will build up to the point where they are more than the pressures we see in the atrium. And that will cause the closure of the atrioventricular valves. And once atrioventricular valves closes, that happens to be the first heart sound. So I'm going to write that pressures in the ventricles are going to exceed the pressures in the atrium. And this will cause the closure of the AV valves. And once AV valves closes, this causes what we call the first heart sound. And the first heart sound, S1, that's going to be the third characteristic. What is the characteristic of the first heart sound? The characteristic of first heart sound is what we call, number one, it is the loudest. When in comparison with S2, which is second heart sound, it is the loudest. Number two, it is longest. It is low pitched in frequency, and this particular one can be heard at best with the bell of the stethoscope. The bell of the stethoscope. So what have we said in ventricular systole, the ECG relationship at R wave and just after T wave? Pressure in the ventricle is more than pressure in the atrium. And we say closure of the AV, this will be to closure of the AV valve. And this happens to be the first heart sound. First heart sound is loudest, is longest, is low pitched in frequency, and is best heard with the bell of the stethoscope. All right. Now, something interesting again happens here. I think let me now write these points here for better, so I don't really have to move so much, and you have to now see everything in one. So let me remove this, all of this now. So what are the points I've said again? Begins at what phase? Which ECG equivalent? R wave, and just after T wave on the ECG. What else have I said? Number two, I've said that pressure in the ventricles begin to build up even more than pressure in the atrium. And when that happens, it causes the closure of the AV valve. What have we said? We have said that because of the closure of AV valve, it causes the first heart sound. And for first heart sound, that was the third point I brought about. First heart sound is loudest, it is longest, it is low pitched, and once compared with the bell of the stethoscope, and is best heard with what? And best heard with the bell of the stethoscope. That's what I want you to note there. Now, remember, this comparison is with S2, the second heart sound. So remember the L's. Loudest, longest, low pitch, and best heard with the bell of the stethoscope. Now, the fourth point is now going to be that pressures are now building up. Now, listen, you get to see something like this. We have our heart like this. I've showed you now this diagram for quite a while now. Now, the pressures that we have here, remember I said that the outflow here, what was the outflow on the right? The outflow was what we call the pulmonary artery. What was the outflow on the left? The outflow was what we call the aorta. The aorta. Now, the next thing that happens is that these valves are still closed. These valves are still closed. As at the stage of ventricular systole. Remember, what are we discussing now? Ventricular systole. So in ventricular systole, we have gotten to this point, and pressures are building up. Pressures are building up. But they are building up to the point where they have still not been able to open these valves. And since they have not been able to open these valves, even with an increase in pressure, the volume remains fairly normal. So that's what I'm now going to say, that even with increasing pressure, these semilunar valves are not open. Semilunar valves are still closed. And because semilunar valves are still closed, this happens to be what we call the state of isovolumetric contraction. The state of isovolumetric contraction that lasts for about 0.05 seconds. Why did I say so? I said the semilunar valves are still closed, but the ventricles are still contracting. Remember, it's a state of ventricular systole. And since ventricles are still contracting, but there is no change in volume because this has not opened or closed. So the volume does not change. So it means that it's isovolume. Iso means same volume, but the pressures, the ventricles are still contracting. So same volume, but with a contracted ventricles. And this lasts for about 0.5 seconds. Now something again happens again, which is the fifth point. Now watch it again. I take a portion, I take one half, and then I show you like this. Let's say this is the half of the heart. Then this valve here was the atrioventricular valve. But now this valve is closed. Now this is semilunar valve here. This is the ventricle, this is the atrium. Now, as pressure keeps bulging, as pressure keeps building up, but we have not opened semilunar valve, we said that step was called what? Isovolumetric contraction. Now, but something quite interesting happens that whenever pressure keeps building up, but without the closure of this, and ventricles are still also contracting, it is going to cause these valves here to bulge into the atrium. So what I said the fifth point is that there's going to be an AV bulge. An AV bulge is seen even without the opening of the semilunar valve. So AV bulge is seen even without the opening, even without the opening of the semilunar valve. Please remember that. It's quite necessary you remember that. Okay? So we have mentioned about 5 points. Now let's go to the 6th point. Now look at the 6th point here. For the 6th point, I think I should show you how this heart looks like. Again, I keep repeating this diagram for your remembrance. What were the outflow tracts on the right? The outflow tracts were the pulmonary artery. What were the outflow tracts on the left? The outflow tracts were the aorta. Now, the pressure inside here is about 10 millimeters mercury. The pressure inside the aorta is about 80 millimeters mercury. So the next point that you're going to make is that we want to forcefully open these valves that are here. And for us to forcefully open these valves, we need to raise the pressures here so much that it is going to forcefully open, because once pressure here in the ventricles increases, it will help forcefully open this, because pressure gradient is necessary for flow. So since these valves here are still closed, now pressure is 10 here or 80, increasing contraction so much, we increase in contraction so much, the amount of pressure or the pressure that are generated here will now increase. So we're going to have a pressure in the right ventricles of about 25 at the end of the day, and the pressure here of about 120. It is these pressures that are able to forcefully open the semilunar valve. So the 6th point should be that increase in pressure on the right. Increase in pressure on the right ventricle. We're going to increase pressure on the right ventricle to about what? To about 25 millimeters mercury to overcome 10 millimeters mercury in the pulmonary artery. While conversely, you are going to also say the same thing. Increase in pressure on the left ventricle to about 120 millimeters mercury to overcome the pressure of 80 on the aorta. It is this overcoming that now brings us to point number 7. And once pressure has been overcome, it forcefully opens it. So this opens the semilunar valve. So I've said different points. Number 1, ECG equivalent from a root wave to T wave. Just after T wave, that's the ECG equivalent. Number 2, pressure in the ventricle becomes more than pressure in the atrium. This was what caused the closure of the AV valve. And closure of the AV valve happens to be the first heart sound. The 3rd point, characteristics of the first heart sound: it is loudest, it is longest, it is low pitched in frequency, and it is best heard with the bell of the stethoscope. Number 4, increase in pressure. What is it going to do with semilunar valve still closed? Is a particular phase called the phase of isovolumetric contraction, which is 0.05 seconds. And we have said, even with that point of isovolumetric contraction, but with pressure not being able to overcome, we are going to have an AV bulge. We say number 6, increase in pressure on the right ventricle to about 25 millimeters mercury to overcome 10 millimeters mercury in pulmonary artery, or increasing the pressure on the left ventricle to about 120 millimeters mercury to overcome 80 on the aorta will forcefully open the semilunar valve. Now, what's the next point now? Once the semilunar valves are open, you can tell me, once this is open, blood now moves out. So that becomes the 8th point, which is going to be the phase of ventricular ejection. So number 8, what I'm going to say here is that ventricular ejection begins, ventricular ejection of blood begins. And when that begins, it is first rapidly, and then it will move slowly. So it will first be moving very fast, and then starts moving very slowly. Then what becomes number 9 point? Number 9 point, so it moves faster, and then starts moving slowly. Number 9 point is to say that amount of blood that is ejected every minute is what we call the stroke volume. So the stroke volume is the amount that we pump out every minute, and this is about 70 to 90 mils. Now, the 10th point should be the amount of blood that remains in the heart. Now, remember, when we talked about atrial systole, I ended by telling you that end diastolic volume was 140. So if you pump out 70 to 90, how much remains? That becomes the thought. So the remainder, which is called the end systolic volume, is about 50 mils. That's when you do 140 minus 90. So that is it here for the 3rd point, the 10th point here of the ventricular system. Very important point. And this is where the bulk of the mark will be. So it is necessary you run these steps. Very important. Now the last thing here, which is atrial systole, early diastole, sorry. For early diastole, what will I say here for early diastole? Number 1 is that the initial step is what we call protodiastole. The initial step is what we call the protodiastole. What happens in this initial step? In the initial step, what happens is that pressures are falling. Pressures in the ventricle will fall so low. Remember we said we belt this pressure to about 120 on the left, or we belt it to about 25 on the right. So pressures are going to fall. They are going to fall so low to the point where they are going to cause closure of the semilunar valve. And it is closure of the semilunar valve that causes the second heart sound. It is necessary you remember that. So the early diastole here has 2 steps. The first step is protodiastole, which we say there's going to be closure of the semilunar valve because pressures will fall so low. And this is what we call the second heart sound. And secondly, at that point, relaxation still continues. So as relaxation still keeps continuous, but with a closed semilunar valve, that step is called the step of isovolumetric relaxation. The step of isovolumetric relaxation. All right, so that has been all the 4 steps here. You can run it through as many times. Now, what are clinicals? Clinicals can mean people that have probably a regurgitation here, either regurgitation in any of these valves. So we call that step mitral regurgitation, tricuspid regurgitation, aortic regurgitation is a problem there. So you can put there, that can cause what we call murmurs. Murmurs happens whenever we have either regurgitation or stenosis. So you are going to say that murmurs due to valvular stenosis or regurgitation. And murmurs happens to be abnormal heart sounds. Okay, so I think that clinical really covers up for so many things. So this has been cardiac cycle at a glance, and I really do hope it makes sense to you and you can be able to reproduce these points for your next exams. Okay, so until then, endeavor to like this video, endeavor to share, endeavor to comment, and endeavor to maybe make recommendations in the comment section. I'll be willing and loving to see them. Until then, do have a nice time. Thank you.